This video will introduce the basics of the phased array antenna for mmWave beamforming. The content includes background information, fundamentals of phased array, basic phased array configuration, and the summary. Mobile wireless communication has shown remarkable improvement in data rate from generation to generation. It is now in its 5th generation, known as 5G, and the expected performances such as high data rate and low latency will completely overtake the previous generation, 4G LTE. However, the true 5G performance can be only reached by using high band, known as mmWave 5G. The low and mid-band 5G use sub-6 GHz frequency band, whereas high-band 5G uses mmWave, which can provide wider bandwidth than any other previous generations. Therefore, we need to focus on mmWave for future communications. Unlike 4G communication, mmWave 5G requires a larger number of base stations to cover the same area. This is due to the intrinsic nature of electromagnetic waves, or EM waves, for which the propagation loss through the air increases drastically as the frequency increases above mmWave band. This loss gets even worse in rainy weather. To overcome the intrinsic loss and maximize transmission efficiency, it is necessary to reconsider how to transmit and receive the mmWave waves rather than spreading EM waves omnidirectionally. Thus, a specific technique is required to focus radiation fields or control the directivity of the EM waves. This technique is called beamforming, but to realize the beamforming technique, the antenna configuration must first be changed. The physical size of an antenna is inversely proportional to its operation frequency, resulting in a larger number of antennas used in the same area compared to sub-6 GHz. Multiple antennas are called an array and used with a transmitter and a receiver that can steer beam direction. Altogether, we call this a beamforming antenna. A beamforming antenna configuration can be roughly divided into two types: switched beamforming and phased array beamforming. The switched beamforming is configured by a switching network and an antenna array. Based on the switching operation, different antennas pointing different directions can be selected to enhance communication coverage, where the beam direction can also be controlled by adding a phase matrix, which can provide different phase combinations to each antenna element in the array. Since this video is only providing a basic introduction to phased array beamforming, we will not cover the details of the switched beamforming. From now on this video, beamforming will be referred to phased array beamforming. Also, phased array usually referred to active phased array because RF chains consisting of active circuits are paired with the antenna elements in the array. Furthermore, beamforming architectures can be also divided into three types. Analog beamforming is the technique where a single beam in a single array is shaped by controlling the phase and amplitude fed into each antenna element. These roles can be performed by RF phase shifters and attenuators or variable gain amplifiers. Next, digital beamforming can be configured by using multiple independent antenna radiations and analog to digital converters, and then processing the multiple signals in a digital domain. Lastly, hybrid beamforming is the combination of both analog beamforming and digital beamforming. Multiple sub-arrays for analog beamforming are combined in a digital beamforming architecture for digital signal processing. Although each type has its own pros and cons as shown in the examples on the screen, the analog beamforming is considered to be the key technology in mmWave communication. Thus, this video will focus on the analog beamforming. As the number of antennas increases, while multiple antennas are combined together in a feed network, the radiating beamwidth gets narrower while the gain of each antenna increases. The relative increase in antenna gain over an isotropic pattern is referred to directivity. Thus, an array antenna has high directivity toward a fixed direction, which is the first step in beamforming. Since the target of communication must be covered over a large area, it is preferable to control the beam directions, and this is known as beam steering. Thus, in phased array beamforming or analog beamforming, phase shifters are added to antenna elements to improve beam steering capability. The fundamentals of steering beam directions can be simplified by the wavefront of plane waves and some trigonometric calculation. Here, we are assuming the elements are equally spaced with equal amplitude. Also, equal phase shift between elements are assumed. Then, if all antennas are in the same phase, the array wavefront will be pointing directly above the antenna array. However, if phase shift occurs among the antenna elements, the direction of the wavefront will be tilted due to the spatial construction and destruction of multiple waves. If we take the two antenna elements and define a triangle with the denoted parameters as shown in the slide, we can calculate the tilted angle with respect to the antenna bore side or required phase shift among the antenna elements in the array. Referring to the simple trigonometric conversion, the parameter L can be expressed in terms of the distance between each antenna element and the sine of the tilted angle from the bore side. Then, considering the time delay as the phase delay of the waves, the required phase shift or tilted angle can be expressed as shown on the screen. Typically, each antenna distance is designed with a half-wave length, resulting in the required phase shift for a desired beam direction angle as the pi multiplied by the sine theta. Consider a 1/4 receive antenna array with a phase shift of delta phi set to each antenna element for a beam angle of theta. Then, due to the phase delay made by each path, only the incident waves from the desired angle will be constructed at the RF in or RF out. Thus, the total array pattern is formed by combination of the element factor and array factor. The array factor of a beam direction theta is expressed by the equation shown here. Substituting the previously defined d and delta phi, the array factor can be expressed in terms of the phase shift between antenna elements as shown on the screen now. If we visualize the total array pattern at a steered angle, a single element pattern and array factor are combined as shown in the rectangular plot. If the number of antenna elements is increased, the beam at the desired direction, the so-called main lobe, becomes sharper and the side lobe levels becomes lower. Also, one interesting factor of the analog beamforming is that as the main lobe angle increases, the side lobe level increases. More specifically, the amplitude of one of the side lobes increases up to the comparable level as the main lobe. We call this side lobe with the largest amplitude as the grading lobe, and this must be suppressed for better beamforming performance. The side lobe is actually related to the antenna spacing d. Referring to the previously derived theta equation, we can re-express the equation for periodicity with an arbitrary number of cycles m as shown on the screen. Then, if the antenna spacing d is larger than the wavelengths, multiple grading lobes are appearing in the ± 90-degree angles, which is undesirable. If the spacing is larger than a half wavelength and smaller than a wavelength, a grading lobe also appears in the ± 90-degree angles as well. Thus, to theoretically reject the grading lobe from the ± 90-degree angles, the maximum allowable antenna spacing is a half wavelength, and this is why most array antenna spacing is set to a half wavelength. So far, we have seen that the multiple antennas with phase shift capability are required for mmWave beamforming. Thus, the overall mmWave architecture is different from the conventional sub-6 GHz architecture, which consists of mainly up and down converters between baseband and sub-6 GHz frequencies. The mmWave front end now requires multiple beamforming chains consisting of phase shifters and variable gain amplifiers or attenuators. The number of beamforming chains is proportional to the number of antenna elements to provide required phase shift and equal amplitude to every antenna element. This functionality is also handled by beamforming IC. You can see an example of 4-channel beamforming IC in the current slide. Thus, the appearance of beamforming IC can be considered as the main architectural difference from the previous generation. Multiple beamforming ICs are directly integrated with antenna elements, and this active integrated antenna array should be considered as a single module to be connected with the following transceiver stages. That is, in mmWave beamforming architecture, the antenna is no longer a standalone passive component, but must be designed and integrated with active circuits like beamforming IC. That's why module integration performance is also considered to be one of the key requirements in mmWave. As the true 5G, which is the mmWave 5G, is being released, and even as 6G is being actively prepared for future mobile communications, many mobile devices in our hands will be supported by beamforming technology. Mobile communication is not the only application, but many other applications such as automotive radar, wireless power transfer, indoor short communication, and sensors will also be supported by beamforming technology, enabling better quality wireless experiences. Thank you.